Welcome to the webinar series by IITACB. So for the new audience, so this IITACB Alumni Center Bangalore provides a unique platform, networking platform to establish a collaboration between academia and industries, and certainly through the project of national importance. So today's seminar is by Professor Jayant Haritsa on a very interesting topic, data science and astrology. Is there a difference? So we are going to hear about the difference. So Professor Jayant Haritsa has joined Indian Institute of Science, Bangalore in 1993, and he is a professor in the Department of Computational and Data Sciences and also the Department of Computer Science and Automation. So he is IIT alumnus from IIT Madras. He finished his BTech and then joined University of Wisconsin for MS and PhD program. And during his scientific journey, he has received many, many awards. I'm just going to mention a few of them. So in 2022, he received Sir C.V. Raman Young Scientist Award, and along with Swarn Jayanti Fellowship, which was also given by the Government of India. And then he is fellow of all the national academies in India. And also he is fellow of ACM, IEEE, and others. He also won Shanti Swarup Bhatnagar Prize, which is given by CSIR India in 2009, and also Infosys Prize for Engineering in 2014. So there are many more. I'll stop here. And so today's talk is going to be moderated by MD Ramaswamy. So I'm going to call MD here. So he's also alumnus of IIT Madras, and then he went to Michigan State University for his master's, and he did MBA from Stanford University. And he began his career at Infosys, and then to a senior positions in various industries. And as the first managing director of Dell International Services in India, he started. And his role was really to basically establish the strategic global hub for technology and customer operation. And then in 2002, MD founded Siltex, a pioneering customer interaction analyst firm that was later acquired by a French group, Activio. So today, MD is an advisor and investor, and that helps to build transformative and impactful businesses. So today's webinar is going to be co-hosted by Dr. Sushila Venkatraman and myself. And for audience, at any point, you can post your question and answer questions or any discussion in a Q&A box, and that we will take up to during the discussion. So over to Professor Haritsa.
Thank you, Abha. Shall I share my slides?
Yes.
Yeah, so is this visible now? Let me just get this set up.
All right. Yeah.
Right. Okay, so thank you very much, Abha, for the very kind and warm introduction, and good evening to all of you. I took the risk of being labeled anti-national by giving a provocative and I suspect unpopular title for this seminar, but it was a deliberate and cheap ploy to generate curiosity and attention. And hopefully this goal has been met considering the participation we see in the audience. But perhaps it would have been, I think it would have been perhaps a more sober and accurate description would be an advocacy for the careful deployment of data science, a tool that has become the buzzword of choice in recent times, especially in the software industry. So the accompanying hoopla has projected data science as the genesis of great and wondrous solutions to all our contemporary societal challenges, whether it be health, transportation, climate, or anything else. However, while it can certainly be a potent force multiplier, data science is equally subject to methodological abuse leading to erroneous and even dangerous conclusions, all concealed under a scientific veneer. So as mentioned in the talk abstract, I'll try to make a case in this talk that data science should be a tool of last resort, not first, and leveraged as a support, not substitute for domain expertise. And in a particularly cruel twist, I will use data to make this case. So a popular view of the evolution of the scientific method is that it has gone through 5 eras. The first is empiricism, where data was simply observed. Then we moved on to theory, where data was explained. Subsequently, with the advent of computing, synthesis of data through programs became feasible, which eventually led to the information age, where data was systematically explored through complex number crunching tools. And culminating in today's world, where we can reason with data, becoming the genesis of science itself. What is interesting to note in this evolutionary process is that the role of data has moved from being the output to now being the input. And while this role reversal is celebrated, it could easily lead us to the worrisome and potentially dangerous situation of putting the proverbial cart before the horse. So let's start with definitions. As per Wikipedia, the fount of all knowledge today, data science cuts across multiple fields using scientific techniques to extract knowledge and insights from a variety of data sources. Now, how is this different from the venerable field of statistics? There, it was largely post facto explanations for observed phenomena, most of which was done manually due to lack of tools, and therefore it was a one-shot exercise on limited data. However, data science, on the other hand, is valued more for its predictive powers, operates on big data, and is therefore by necessity both automated and iterative. But still, what is important to remember is data science is still statistics on steroids. So here is a more humorous take on how statistics has morphed to data science over time. So you start with the base statistics, and then you can see in the picture here, if when you're implementing, it's called logistic regression. When you're hiring, it's machine learning. And then when you're fundraising, you elevate it to AI. So we in India are rather fond of crediting to ourselves all the major advances in human progress. And you would be familiar with things like plastic surgery, magnetic levitation, and so on. But for the most part, this is just wishful thinking. However, you might be surprised to know that with data science at least, some legitimate credit can be claimed by the ancient Indians. In particular, this notion of computational positivism, which was studied and evangelized by the late and much celebrated Professor Roddam Narasimha, patron saint of the Indian aerospace mission. The core thesis of this classical approach, which he described in an article called Axiomatism and Computational Positivism, which appeared in the Economics and Political Weekly about 2 decades ago, was to make computation match with observation. And this was referred to as Drigganita Ekya. And this was initiated in the world of astronomy by the ancient Indians. Now, this approach to science, interestingly enough, was diametrically different to the competing Greek or Hellenic approach, which was based on a logical and axiomatic development of models and theories. Whereas in the Indian approach, the focus was purely on obtaining consistent and accurate quantitative predictions of observed phenomena. So essentially, it was Aryabhatta versus Ptolemy. And in a nutshell, the Indians asked what, whereas the Greeks asked how. So in data science, we see a similar trend, and this mechanistic approach works well with natural phenomena, where patterns are regular and repetitive. But in today's man-made world, where randomness rules the roost, one must apply data science with care. So in the rest of this talk, I will provide a few highlights of the so-called good, bad, and ugly of data science, and with particular emphasis on the bad and the ugly, since they go against the prevalent wisdom of data science being a universal panacea for all ills. But let's, in the interest of fairness, start with the good stuff. So for starters, data science can certainly be an extremely effective tool for building models with strong quantitative confidence. And it has been used successfully in diverse areas, including equipment monitoring, transportation planning, rate determination, and targeted advertising. So for instance, the huge oil company Shell has built an analytics platform to run predictive models to anticipate when oil drilling machine parts might fail. And those of you who are familiar with the oil industry would know that unlike computers, where you can do a control alt delete and restart the system, in an oil platform, if you have to shut it down and start it again, it takes weeks or months to do it. It's an extremely complicated and cumbersome job. But thanks to the predictions from data science, their inventory analysis to take preventive care for these kinds of potential failures has been reduced from days to hours. And in the process, millions of dollars a year have been saved on the cost of inventory management. Similarly, RRD, which is the communications giant, has been able to predict freight rates well in advance with high accuracy, despite there being extremely complex variables such as weather, geography, and driver availability. And through this, they have been able to find the ideal shipping rates. And finally, and probably most importantly, data science has proved to be an invaluable tool in analyzing human health conditions. So for instance, although we have a plethora of imaging tools, X-ray, MRI, CT scan, and so on, which are all meant to visualize the inner parts of the human body, traditionally, doctors manually inspect these images in order to find irregularities. But they find it difficult, for obvious reasons, to find microscopic deformities, and therefore, only when these become much larger are they able to come up with a diagnosis. However, with deep learning technologies, such as image segmentation, it is now possible to even find these microscopic deformities well in advance and thereby provide excellent prognosis of nascent diseases before they reach an irreversible state. While all this is good and dandy, unfortunately, data science has become the victim of its own success. And this has led to enormous hype and wild claims, especially in India. So the casualness with which data science is approached is immediately evident from the ubiquitous training advertisements in the popular media, pushed by a plethora of schools, where you see statements like, become a data scientist in 3 months, no background required. And in fact, it's not even that you have to be there for the entire 3 months, it's only on weekends. You can keep your regular day job during the week and then just attend these boot camps on weekends. And what is the outcome at the end of the 3 months? You become a master. You become a master of all 3 elements of data science: statistics, computational tools, and business knowledge. And as a bonus, they also give you professional assistance and guidance on how to craft your resume. Perhaps this is where most of the time is spent. But if you thought even 3 months was too short, look at this more recent advertisement. It says, become a data scientist in a day. And not even the full day, just 10 hours. So you still have time for Netflix and Amazon Prime as well. Okay? So essentially, it's like Cinderella. You dramatically, at midnight, you transform yourself into a data scientist. You require no background, and suddenly you're up and running because you have the ability to take a Python program, use some data, and come up with some conclusions. There was also a magazine survey that was done a couple of years ago that went and asked in the industry, saying that now data science is being ubiquitously used across a variety of, and spectrum of sectors. So data scientists are expected to have a broad set of skills. What are the most important skills? And the answer that came back from this survey was that there were a variety of software tools, for example, the Python programming language, or the visualization software called Tableau, or the R Studio, which is an integrated development environment for the R, which is a statistical computing programming language. And you have to have an in-depth knowledge of Hadoop, which is used for distributed data processing. And they said that knowledge of these software tools was crucial. What is amazing and conspicuous by its absence is that domain expertise and scientific foundations, which should have been top on the list, are not even seen here. So nowadays, we have all these pithy one-liners that data is the new oil. Or if you want to appear more intellectual and more erudite, you say that data science is the new quantum mechanics, forgetting that Richard Feynman, who was the father of quantum mechanics, used to himself say that anybody who claims to understand quantum mechanics actually doesn't do so. My own formulation is based on Remo D'Souza, the well-known choreographer, who had this acronym called ABCD, that is, anybody can dance. And what I would transform it into is ABCD actually today stands for anybody can do data science. So the reality for data science is quite different from the myth that surrounds it today. And what is most important to understand here, and is the crux of the matter, is that the key word in data science is not data, but science. And data science requires a deep understanding of the underlying physical and mathematical principles, as well as the data domain, and not just programming tools and environments. If you simply did analysis from data because you had the computational wherewithal, and without having these other prerequisites of understanding the domain and understanding science, it is very likely to produce fraudulent answers. And this was captured very pithily by Ronald Coase, who was the 1991 Nobel laureate in economics. And he had this wonderful statement, which said that if you torture the data long enough, it will confess to anything. And in the remainder of this talk, I'll show you several such examples. And one of the reasons that this happens with amazing regularity is that we all come in with preconceived notions when we do research or when we do analysis. And we have these subconscious biases and desires. And in a sense, we want to will the data to match with those prior biases. We do not really come in with an independent mindset. We have a favored outcome. And the moment that there is some suggestion that the data is matching with that outcome, we are very willing to grab it without asking further questions. So over the past decade, there have been quite a few books that have gone against this hype and essentially spoken truth to power. And a few that I have found particularly thought-provoking are shown in this slide here. The first is Weapons of Math Destruction, which is a nice pun on the weapons of mass destruction that we had during the Iraq War. And this is by Cathy O'Neil of the Wall Street Journal. And this appeared in 2016. And I'll be showing you some examples from this book later on. This was then followed by another book called Calling Bullshit. And this was by Professors Bergstrom and West from the University of Washington at Seattle. This was in 2020. And the latest, which has just appeared a few months ago, is AI Snake Oil. And the authors of this book are Arvind Narayanan, who is a professor of computer science at Princeton University, and Sayash Kapoor, who is his PhD student. And interestingly, for this audience, both Arvind and Sayash are IIT graduates. Arvind from IIT Madras in 2004, and Sayash from IIT Kanpur in 2019. So in the rest of this talk, I will use examples from these books as well as other sources to showcase how data science can be deceptively and extremely problematic in its deployment. But before that, the organizers had recommended taking a short break for questions. So I will hand it over to the moderator, MD Ramaswamy, with whom I had the privilege of being both his schoolmate here in Bangalore, as well as his batchmate at IIT Madras. So with that, over to you, MD.
Thank you, Jayant. That was beautifully set up. I can't wait for your second part of this presentation. Let me just check Q&A there. Guys, you can put up your questions here in the Q&A box as Sushila suggested. So where you can put your questions at any time, by the way, because we're going to have a bunch of question answers at the end as well. But in the meantime, Jayant, I just have a couple of things to kick it off.
Sure.
You did talk about I think the second, third, or fourth slide, you talk about the kind of competing methodologies, where you gave the example. Where one was, kind of like the data science, which you talked about, where you kind of use the input to kind of fit the output or fit the results. Whereas the competing method, the what versus how. Now, you did give some fascinating examples also where data science has really worked, like the oil industry one and the medical one and so on. In this case, do you think the traditional method could have worked?
It's, I think, unlikely that the traditional methods could have worked because the physics of an oil plant is extremely complicated. So while you do have all those physical laws and you could apply them, getting it to be done on a very large system with many interconnected parts and correlations across many variables may become hard, because if you remember, even in most of the physics and math that we learned, they were under idealized conditions. So we would do all these free body diagrams, assuming there's no friction, for example, on the surface and things like this. And that was just because it was computationally or analytically very hard to come up with answers if you had to take all the detailed variables into account. But I think what you could do is to use all the natural laws to give you a qualitative feel as to what should be the behavioral trends. So for example, should it be a quadratic curve, or should it be logarithmic? Should it be concave? Should it be convex? Those can be obtained from the natural sciences. But to actually predict real values becomes very difficult because most of them are founded on some idealized version of the world. For example, even in queuing networks, we assume that all arrivals to a process are independent. But if you go and look at the Bangalore traffic, you know that there's no independence across any arrivals to a traffic junction. So in that sense, if we take away all these assumptions, then getting the right values may become hard. But at least what we could use the natural laws for is to say that, is this behaving qualitatively the way that I would expect it to be? That should this be going up or down? At least if we can check that and kind of what kinds of polynomials are being used, even though we don't have the right coefficients, that would at least give you some degree of sanity that you are at least on the right track and not violating Newton's laws of motion, which we regularly do in coming up with our predictions.
Yeah. So does it mean that, when you have, like you gave the example of, natural science and behavior, like climate and so on, does it mean when there's complexity in the relationships in the data, then you use the data science, the science part of data science? Is that a kind of a fair generalization?
Right. I would say that you can use the data science to quantify hypotheses that you had already made before. So my complaint is that you don't allow the data to dictate your thinking process. You already have a seed of an idea saying that there may be an El Nino effect or something like that happening, or you might be thinking that there's a global warming occurring, and you have some sense of where this is happening and why the glaciers are melting and so on. And subsequently, the data is very useful for two things. One is to validate your hypothesis, and the other is to give it a quantitative flavor. But if you start with the data itself without having anything in mind and just ask it that, oh, great database, give me something interesting from this sea of information that you have, it's very likely that you don't understand in a sense, the internal dynamics of why this data came about. And you are just looking at it superficially and just taking the values and then trying to come up with some kind of hypothesis for it. So my view of data science is that it should come in at the end after the human has done the thinking and has a gut feeling that this is what I expect should be the case. And now let me use the data to either validate or in a sense, contradict the hypothesis. And in addition, if it does validate it, it may give you some quantitative values of saying that, yes, this is a quadratic curve and the coefficient is 4x squared instead of just being proportional to x squared. So something like that could be done. But it should be at the tail end of the pipeline, downstream, and not as the starting point, saying that I don't know what is happening here, but because I have a sea of data, hopefully something will emerge magically out of it and I like it.
Okay, great. Thank you. Okay, a couple of questions have come up. First one is a simple one. Actually, Sushila can answer it. Maybe get the presentation of the PPT after the webinar. Is the answer
sure.
yes?
Yeah,
Okay.
sure. That should be fine.
Sure. So the answer is yes to that.
Right.
Second question is, do you actually think there is a paradigm shift vis-a-vis where in the cycle of the scientific method we begin new investigations nowadays? In brackets, you alluded to data transitioning from output to input. Kepler was able to deduce his laws only because of Tycho Brahe's extensive and exquisite measurements. This is right up your alley.
Yeah, right. No, it's absolutely true. You can, but the question is that where does the reverse engineering start? So all the earlier astronomers already had a feel. So I always like to kind of advise my students that it's not the brain which is most important in research. It's your stomach. That's what's your gut feeling. So they already had a sense of how things were behaving, and then they were using all this data to do reverse engineering to figure out exactly what kinds of equations were required for the elliptical orbits and stuff like this. But it's not that they came in ab initio and just said, I don't know anything about it. I just have a program. Let me throw it on the data and hopefully something magical will emerge from it. That's the concern that I have. That is, where does data science play a role in the pipeline? It should not become a substitute for human intuition and human thinking. It should become an aid. And we see this also in almost all the tools, that AI tools nowadays that are being marketed. They always call them as a co-pilot or an assistant, or some word is being used like that. Correct. To showcase that the human is still under control, but this is a value-added tool that can support the activity. But we should not outsource thinking to the machine. And to give you a simple example, we find this all the time with our students nowadays, is that often they give us values, for example, the execution time of a database query, and they will write it as 4.678743265 to about 16 or 18 digits after the decimal place. And I keep asking them, in Physics 101, you already know that you cannot have better accuracy than the measurement instrument. And how did you get so many digits after the decimal point? And they say the computer gave it to me and I cut and pasted it, which means that you're not thinking of the physics at all and you're just blindly doing cut and paste. So that kind of a dangerous paradigm is what we have fallen into, especially in computer science, is we have stopped thinking. We say that whatever gets spit out by the machine, we take it as essentially gospel truth. And skepticism, I think, is the most important requirement for a researcher.
Okay.
And
right. Okay, fine. I'm going to just, I think for one last one, it's more a comment. You can comment on it as well. I think you're being too optimistic, Jayant. That's what he says. I predict that you hear the most is precisely where we are heading. In 10 years, we will be doing blind data in and out. He's just extrapolating the trend, Jayant, which you fear.
Fear. Right.
Anyway, okay, great.
Yeah, hopefully all this, at least the people who are on this call would serve
Would be the
to
change
prevent
agents.
that from happening. Yes, right.
They'd be the change agents. So all
Right.
the folks listening in, you guys have a homework to do. Okay, with that, Jayant, we'll close the Q&A at this point. You
Sure.
can continue with your second part, and for
Okay.
all the folks listening in, please post your questions. Continue to post your questions in the Q&A box, and we'll pick it up after Jayant finishes. Thanks.
Okay, so I'll share my slides again. Yeah. Okay, so now we will move on to the more exciting part. Several instances where data science has gone wrong due to methodological errors. So there was a particularly thought-provoking article which appeared in a op-ed article of the New York Times. This was in about 10 years ago, April 2014. And the article was by two faculty from New York University, Professors Marcus and Davis. And the title of the article was somewhat sarcastic. It said 9 problems with big data. And the point that they made was that big data is prone to giving scientific sounding solutions to hopelessly imprecise questions. And as a case in point, there was a study that was done jointly between MIT and Google. And what it tried to do was to quantitatively rank historical figures regarding their impact on the world. We all love ranking, of course, and what they came up with was who's bigger, where historical figures really rank. And what was astonishing was that in their list, Hitler outranked Aristotle. And I think Aristotle must be turning in his grave at high angular frequency at this gross insult to his contributions. And the only reason that this happened is that there's a lot more web pages about Hitler than Aristotle. What is even more important, apart from the methodological problem, is that such analysis should not have been attempted in the first place, because it completely lacks a sound basis for comparison. And this is analogous to the dismal emptiness of our university rankings, which everybody gets very excited about, but actually trivializes transformational interventions. But these unfortunately play a big role in today's public and administrative perception. All the IITs are always worried about where are they being ranked in either the Times ranking or the NIRF rankings and so on. But all these rankings are actually absolute nonsense. You cannot change large elephants overnight. And institutions change slowly and steadily. And also what is most important is that you should be looking at in what way has the student been transformed from what they came in with the kind of intellectual abilities they came in with, and what did they leave with. So for example, just in Bangalore itself, there was a very famous college, or still is there, called NMKRV College. And they had a very interesting model. They said that we will take only third-class students and we will transform them into first-class students. Whereas all the other colleges were just cherry picking the best. And of course, those people who continue to do well with or without the institution. This NMKRV college, and was run by a person, a very famous educationist in Bangalore called Cheena Mangala. She said that I want to transform students from third class to first class. Now, what kind of ranking can you put on such an exercise where you have essentially changed the entire nature of education? So education is not a game. It is not a sport. Okay? It's a process of self-discovery. But we still want to go ahead and do rankings of institutions, which I think is a completely incorrect exercise. So not only in this example also, not only is the methodology wrong, even the starting question is incorrect. So in a nutshell, the claim is that big data encourages you to ask the wrong questions. And therefore, we need to consciously ensure that big data does not become huge nonsense. So these methodological problems with the data science practice have actually prompted a very curious course. This is a formal course in the University of Washington, Seattle, very well known in computer science. And this is by Professors Bergstrom and West. And the goal of this course is specifically to highlight these blunders. And I'm not making this up. This is actually a 3-credit course. And the title of the course is Calling Bullshit in the Age of Big Data. And if you look at the course description, it says that the motivation is that traditionally, highbrow nonsense used to come couched in big words and fancy rhetoric. But more and more we see it presented instead in the guise of big data and fancy algorithms. And subsequently, the book and the course go on to give several such examples. I'll cover a few of them here, but I would highly recommend you to go and look at that website as well as the book. So let's start with a simple example, which is from the advertising domain. So here you can see that Nestle is proudly announcing that their dark chocolate is 99.9% caffeine free. And you would think, wow, that's really good. But the reality is that even strong coffee, Starbucks, is 99.9% caffeine free, since caffeine is a very potent drug, even in small quantities. So now you might say that, hey, look, we all know that advertising is the art of spin, so you shouldn't even be taking this seriously in the first place. Fair enough. Now let's go to the other extreme, to a more academically sound example. So this is about a paper that appeared in Nature, which, as most of you would be aware, is the most prestigious scientific journal in the world. And this article by Tatum et al. In 2004 looked at the medal winning times, that's the gold medal winning times, for men and women in the 100-meter dash in the Olympics. And what they did was to analyze this data over the past century. So the graph that you see here is that on the x-axis, you have the years starting from when the modern Olympics started, which was around 1896. And then you have a value every 4 years. And on the y-axis, you have the completion times, okay, or the winning times. And as you can see that initially it was around 11 seconds for men. It has come down to around 9.8 or so. Similarly, for women, it was around 12.5. It has now come down to around 11. Okay. So what the interesting question that they asked themselves is to say that, look, we have all this data. And yeah, so the blue dots are for men and the red dots are for women. They said that, look, we have all these points. And it is extremely interesting to see if we can fit a regression line to this, in particular, a linear regression here. And we cannot resist the temptation. Let's go and fit linear regression lines to this data. And those linear regression lines are the red line that you see here and the blue-green line that you see below. And the question that they really wanted to ask is, when will women become faster than men in the 100-meter sprint? So what they did was to extend this line here, as you can see, similarly extend this line here, and there is a crossover around 2156. So the claim is that in about 125 years, women will beat men for the first time. But there is a fundamental mistake here. It is highly unlikely, knowing body physiological characteristics, that improvements will continue in a linear fashion for the next 100 years. Instead, it is much more likely that the performances will plateau out after a certain point, and the subsequent improvements would be marginal. Such errors, which are well known to statisticians, are called right censoring. In fact, there was a very humorous comment on this paper, which said that, why did you guys stop here at 2156? Why don't you continue this line until it crosses the x-axis? Because you are free to draw the line further. And the claim now is that in about 500 years, you may have times of less than 0 seconds. That is, you finished the race before it even started. And even Usain Bolt would have had a hard time to match that. Okay? But the point that is trying to be being made here is that if we just ignore reality and simply work backwards from data, you are going to come up with ludicrous results. In fact, you could also go the other direction and say that suppose I went back to the original Olympics, which was in 776 BC. the winning time would be around 40 seconds. And I think I could also have managed that. So with data, you have now succumbed to the temptation of fitting a line to it and thereby coming up with answers that are clearly impossible from knowledge of medical physiologies. But as you can see, the goal here was to show that at some stage women could beat men. And therefore, this is a preconceived notion where you are very keen to be able to show it. And therefore, you throw science to the winds. Okay, so the next one is even more interesting. And I absolutely love this particular example. There is a research paper written by Professor Diana Kenny from the University of Sydney, again, a very well-known institution. And the title of the article is Music to Die For. And in this case, it's actually meant literally. They're looking at when do musicians die based on the genre of music that they were playing. So the data that you see here is that on the x-axis, you see different genres of music, starting from the oldest, and this is all, of course, Western music. So things like the blues, jazz, country, and so on. And then as you come later in time, you come to heavy metal, rap, and hip hop. On the y-axis, you have the average ages at death of two groups of people. One is what is the average expectancy for women, which is the orangish line that you see here, and for men, which is blue here. So that's roughly around the 60 to 70 mark. This is for the average population. And then the thick lines that you see here, the orange and the blue, this is for musicians, based on which kind of music they're playing. And what you see here is that those musicians who are in the classical types like blues, jazz, country, and so on, they live to a ripe old age, at least around 60 years. And this is similar to the general population at large, is what you see here. But as you come to the newer styles of music, and especially when you come to metal and rap and so on, you see that there's a steep decline here, and that these musicians are prone to early demises just around 30 years. And in fact, when this study was published, the Washington Post said, this is worse than war. We don't lose half our army in a battle. And what is even more interesting is that at first glance, this data actually fits in with our preconceived notions, because we always think that these newer styles of music, heavy metal, rap, and so on, that most of their musicians are living bohemian and licentious lifestyles. And these are stereotypically associated with this group as drugs, alcohol, loose morals, and so on. And therefore, it's essentially the subtext here is that you deserve to die because you are living a dissolute life. But actually, the truth here is that the study is fundamentally flawed from a statistical perspective. And that is because the musical genres like rap and hip hop are new styles of music. So what the data does not showcase here is the long-term age at death, but only of those musicians who happen to die early. You have to wait another 50 years to look at all the long-living rappers and hip hoppers. But mathematically speaking, what has happened here is that transient behavior has been confused with asymptotic trends. And then the media, of course, converted the average age at death, which is what is the observed values, to a predicted value to saying what is life expectancy. And as I said, everybody was very happy looking at this data, saying that we told you so, that all these new guys, new musicians are actually living a bad lifestyle. And in a sense, they therefore deserve to die early. So if you map it to the Indian context, on this left-hand side, you have bhajans, Carnatic music, Hindustani music, and so on. On the right end of the spectrum, you have Yo-Yo Hari Singha. Okay, so the mathematical error that is being succumbed to here is that we are confusing the old chestnut of correlation with causality. So we are trying to associate musical genre with the age at death. And further, this correlation is a consequence of two other correlations shown through the missing variable in this blue box. And because the authors of this research paper missed this variable, they came up with completely bogus conclusions. Okay. So let's move to transportation now. Very interesting situation occurred a few years ago, and this was with regard to the rankings of the US airlines. In 2020, Allegiant Airlines was ranked the very best and American is the worst. But in the previous year, it had been exactly the opposite. American was the best and Allegiant was the worst. So if you look at this, you might say, oh, wow, maybe the Allegiant management took the bad 2019 ranking to heart and transformed the company. Whereas in American Airlines, the management became complacent, resulting in the precipitous drop in reputation. But actually, the reason is much more mundane. In the rankings, there was a baggage safety parameters related to number of losses of baggages of passengers. In 2019, the parameter was the losses normalized to the number of passengers that was carried by the airline. In 2020, they changed this parameter to the same losses, but now normalized to the number of bags that were being ferried by the airlines. And what they found is that Allegiant lost less than 2 bags for every 1,000 suitcases that they ferried with, for their passengers, whereas the industry average was about 3 times higher. But before you start congratulating Allegiant, you should also know that Allegiant is actually a discount airline that charges very heavily for checked-in baggage. In fact, often more than the ticket itself. Therefore, Allegiant passengers often don't check in any bags at all. So if there are no bags, you really have nothing to lose. And that is the reason that Allegiant got this very good performance. And thanks to this parameter, which was extended into the rankings, now you had a complete reversal of the best and worst airlines. Nothing has changed, but you just look at the data differently, and you are now shown diametrically opposite outcomes. In fact, there's a very nice book by Professor Raj Jain, who was a former alumnus of IISc, which says that, which the title of the book is The Art of Performance Modeling. And he says that give me any 2 systems you have, A and B, and you tell me which one is supposed to be better, A or B, and I will construct an experiment that will actually showcase that outcome. So therefore, you can see that science can be easily molded to fit whatever outcomes you desire. There's an even more subtle case that you see in this particular slide. This relates to research grant allocations. And this is from the National Institutes of Health in the US, which is similar to our Department of Biotechnology in India. And the graph that you see here on the screen has on the x-axis the number of projects given to an individual investigator. And on the y-axis, it shows the site that what you see here. It shows the citation score for that particular investigator from these projects. So essentially, this is a return on investment graph, which shows that as I give more and more projects to a particular investigator, what is the return in terms of citation counts for them. And the behavior that you see here is that there are decreasing returns with each additional project given to an investigator. And on the surface, again, this makes perfect intuitive sense. If a researcher has more projects, they are spreading themselves too thin. They do not have sufficient time to devote to each of them. And what is the proof? The proof that NIH said was, look at the concavity of this ROI graph. And using this graph, they justified capping the maximum number of projects given to an individual investigator to be at this point, which is roughly around 4 or 5 projects, and saying that we will no longer give you 9 or 10 projects. We will stop at 4 or 5 because we know that subsequent to this number of projects, you are actually not going to be having sufficient time to devote to these projects, and therefore your performance is going to become weaker and your citation count is going to go lower. But you may not, again, all this is very intuitively appealing. But what you may not have noticed, and I didn't tell you so far, is that both the x-axis and the y-axis are on a log scale. And concavity in the log space does not imply concavity in linear space. And further, extending composite results, that is over aggregates, to predict individual behavior is completely incorrect. Because right now we're saying that anybody who is given 7 projects will do poorly. That's not the case. Over many different investigators who are given 7 projects, some have done poorly. But it does not mean that a particular investigator may not be able to do very well even with 10 projects. Okay? So extending composite results to predict individual behavior is completely methodologically flawed. It is no different to attributing stereotypes of a general population, even if it is true, to every individual of the community. And this is a common error that repeatedly surfaces both in our civil society and our popular media. Okay, so now let me show you a different kind of a problem that has actually occurred in the scientific domain, and this relates to chemical reaction. So there was a paper in the journal called Science, which along with Nature is again one of the most prestigious journals in the world. And this was in April 2018 by Professor Annemann and others in Princeton University. And the research is on predicting reaction performance in carbon-nitrogen cross-coupling using machine learning techniques. And what they did was to study the impact of isoxazole additives on reaction poisoning during book-walled Hartwig coupling, which is a very popular technique in pharmaceutical drug synthesis. And what Professor Annemann and his team said is that we have used an advanced machine learning technique. So not just linear regression, we have used an advanced machine learning technique, which is called as decision forest, where you have an ensemble of classifier trees. And this worked much better than linear regression. And we have successfully applied it to both sparse training sets, because for wet lab experiments like in the chemistry domain, it's hard to get too much data. And it's also been good for doing out of sample production. So when you went from training to testing, it did very well. So now on the surface, this looks like a poster child for machine learning, saying that you have been able to extract the essence of reaction poisoning, and now you're able to predict what kinds of reactions and their performances will happen when you look at carbon-nitrogen coupling. But just 6 months later, in the same journal, so you can see that this is in November 2018, there is a comment by Professors Chang and Kaiser. This is now from the University of California at San Francisco. And they said that we did a very simple experiment. We replaced all the measured values of the chemical features, like the NMR shifts or the dipole moments of the atoms and so on, with just random values. That is essentially we threw garbage at the model. But even if we did so, it had similar performance to the Princeton outcomes. So what this means is that the model wasn't doing very much. The reason that it was behaving so well was there was a hidden structure within the data set. So the importance of additive features cannot be distinguished from this hidden structure that already occurs within the data set. So what the Princeton folks should have done is to always have a sanity check, saying that if I throw in garbage, do I still get the same results as with meticulously calibrated values, in which case then it means that there are other features in the model that are essentially agnostic or impervious to what you are feeding it. And those are the really important features that dictate the performance. Okay? And so you can see that it's not just in the advertising domain or in the popular media. You can see that the best of scientists from the Ivy League colleges are also making essentially textbook mistakes in handling statistics. Let's come to global warming. There was an interesting study, again in the Nature publication. This was in 2010. And the study was on what do you expect the rise in sea level due to global warming. And what these people did was to look at temperature and coral data over a very large period of time, 22,000 years. And using this prior data for the last 22,000 years, they said that we will predict the sea level rise will be by almost about 3 feet by the year 2100, which means that essentially goodbye to many of the island countries, including the Maldives and maybe Lakshadweep and so on. But subsequently, there was this obviously caused a lot of consternation, because it said that in another 50, 60 years, we will have a rise in the sea level by 3 feet. The author said that since publication, we have now become aware of 2 mistakes which impacted our estimates. And in fact, it's impacted them so much that we can no longer draw firm conclusions about the observed behavior. And the first mistake was just a plain old miscalculation, but the other was more subtle. It is said, what they did was that they did not account for the temperature change over the past 2000 years, and therefore came to erroneous conclusions. And due to these methodological errors, they had to actually retract the paper. And they also said that we'll now invest in the future work needed to correct these mistakes. Let's look at a different example from science again, earthquake predictions. Okay? Everybody would love to do it. So there was a competition which was run by PNAS, which is the National Academy of Science in the US. And they said that let's try to do earthquake forecasting and let's make this a machine learning competition. And basically they provided all the data, which was seismic signals recorded on a piezoceramic transducer. And there was lots of such data given to all the people who participated in this competition. And in fact, the number was very large. There was close to 5,000 teams which evaluated this training data on the Kaggle platform. So if you remember Charles Richter, who is the founder of the Richter scale, he said that only fools, charlatans, and liars predict earthquakes. But still, I think it's the human tendency to say we would really love to predict things. And although we are a long way from earthquake prediction and forecasting, we would like to believe that recent work in the laboratory quakes offers a glimmer of hope. What were the primary features of this winning submission in this competition across the 5,000 teams? First, just the number of peaks in the denoise signal. So if you look in the previous slide, you see that there are lots of peaks here, which is the target time to failure versus the experimental time. And all they did was to compute the number of peaks. They took 20 percentile on the standard deviation of a moving window. And they also looked at the 4th and 18th MEL coefficients, which is a very standard, this is the MEL frequency Kepstrel coefficients. This is a very common statistic used in audio processing. So they just looked at these 4 features, because normally you would expect that for an earthquake, you would have very large number of features that would be required to figure out these things. But they found that the winning submission had just 4 features, and that worked well enough. But what was even more surprising and interesting is, and they write it somewhat sarcastically, is that there was amazing intellectual diversity that was attracted by this competition. There were teams comprised of cartoon publishers, insurance agents, and hotel managers. And in fact, none of the competition winners came from the domain, which is geophysics, which means that either the data is not of much value and therefore all the scientific ideas that the geophysicists had do not apply to the laboratory, or that the geophysics people also succumb to the same mistakes in analyzing data. Let me also show you another example from the health domain. And this is a pneumonia protocol, which was looked at in 1997. So at that time, doctors had to figure out that for a patient suffering from pneumonia, should they send them immediately home after treatment during the day, or should they admit them to the ward and make them stay overnight so that they can monitor the status of the patient. And in the case of high-risk patients, that is those who are old or have asthma, then we can send them straight away to the ICU. So the expectation was that if I have a large amount of data, I can substitute the doctor's decision with an AI-based decision, because our expectation is that given this large amount of prior knowledge and data, the model would be able to make a better decision than individual humans. What is interesting is that the model came up with a recommendation that what would have expected to have been high-risk patients, as patients with asthma, it actually claimed that they have a lower risk of complications. So we recommend it that you send them home immediately. Now, this is completely counterintuitive because people who have asthma are much more likely to have complications and difficulties in negotiating pneumonia. But the model is saying the opposite. What's the explanation? The training data collected by the hospital was under the earlier existing decision-making system, which was that asthmatic patients were sent straight to the ICU. They weren't even sent to the ward. Straight away from the registration desk, they went to the ICU and therefore received better care, and the outcomes were good. So in this case, the model's predictions are actually correct, but they are correct under the existing system. But the goal was to use this model to replace the existing system, in which case all its recommendations become invalid. Okay? So you can see that there are fairly subtle and nuanced kinds of mistakes that one can make. And therefore, it is very important that when you do a data science-based study, that you do understand the science behind it, you are skeptical about it, you have earlier hypotheses, and make sure that the data does not violate Newton's laws of motion. So far, we have been looking at examples from Europe and the US. So, and you might say, oh, well, maybe those guys don't know how to do data science. Well, we in India, we become data scientists in just 10 hours. We are the best in the world. Okay? So let's look at COVID. And let's look at the Sutra model, which was actually supported by the government. And there's a very detailed article in the Hindu newspaper from Chennai. This is in May 2021, which talks about why the Sutra model got so many things wrong. And if you look at the description, it says that unlike many other epidemiological models that extrapolated cases based on the existing number of cases and how the virus behaved, how it spread, the Sutra model said we will choose a data-centric approach. But the problem is that the equations they came up with based on a purely data-centric approach were extremely brittle and volatile, and therefore even the equations couldn't tell when a constant changed, and these numbers were changing at a very fast pace, and it depended on the number of infections being reported and so on, all of which had some degree of noise in them, and therefore the Sutra model could not even guess the second wave where you saw that there was a stupendous spike in the number of COVID cases. And you would see that there were many models that were, it's not just a problem with Sutra, there were many models in India that were created at that time. Almost every academic institution had their own models. In fact, in the IISc, we had multiple models from different departments. And the only thing that was common across all these models is that all of them were wrong. None, repeat, none of them predicted the second wave, which was a complete extreme case of COVID infections. So now one might ask, how did this happen? Because if you look at the people who were behind Sutra, they are some of the legends of control theory and computer science in India, some of the most famous names, technically absolutely brilliant. But the danger is that they said that we are great computer scientists, we know how to handle data, we don't need the scientists. So if you look at the Sutra team, they did not have epidemiologists. They had very good computer scientists, they had control theorists, they had data analysis folks, everybody was there except the scientists. And because of this, they came up with a model that relied on too many parameters. And due to this, having too many parameters usually run into the danger of what is called as overfitting the machine learning community. And they fell prey to it, did not realize what was happening. And only much later, when they looked at it in hindsight retrospect, realized that they had made a basic mistake. So if you had included a domain scientist in the team, then hopefully you would not have had such egregious mistakes being made. Okay, now let's look at, apart from just making erroneous predictions, there is also a danger that incorrectly created and applied data science platforms may actually cause harm to the intended recipients of the services. So there is, as I had already shown you earlier, there is a book which is very appropriately titled Weapons of Math Destruction by Cathy O'Neill. And this provides a detailed treatment of how data science actually increases inequality and threatens democracy. So you don't need Trump for it. Data science is good enough. Since our lives will increasingly depend on our ability to make our cases to machines which lack independent judgment and contextual understanding. So here is an example where data science actually adversely impacted the most vulnerable section of society. So in Australia, there's an organization called Centerlink, which is meant for administering welfare. That is essentially giving financial help to those who are below the poverty line. And there is an automated compliance system which compares the income that is reported by these recipients to the information held by the taxation office. So now most of these people who are below the poverty line are seasonal workers who usually get work in the summer because they are doing fruit picking or harvesting and so on, and often don't have work for the rest of the year. But what the automation system did is that it took the wages that were earned by these seasonal workers during the summer and extrapolated them to the whole year and said, "Wait, these guys are actually earning quite a lot. So they really don't need help from the society. And they are actually, this is a fraud where people who don't deserve it are getting support from the government in terms of financial help." And due to this, it said all these recipients will be blacklisted and will not be given the money. And several legitimate recipients were unfairly deprived of their state legislated benefits. Something which is of particular danger with data science is you can now get into the quicksand of self-fulfilling prophecies because it can now propagate through a system. So for instance, if you go to a bank and that particular bank, because of a faulty risk model, tells you that we won't give you the loan because we don't think you have sufficient collateral or guarantees that you will repay the loan. Next, you go to a different bank, hoping that you get a better outcome there. It is more likely to be denied again because now it is on record that you have been refused credit before. Perhaps this may not have happened in India for a particular bank, which is called as Yes Bank, because they have no choice but to say yes. But in general, there is a trajectory of information that is being maintained. And therefore, once you go from bank to bank, each successive denial makes it more likely that the subsequent bank will also say no. And especially if they know that the other banks have said that this person does not qualify for a loan, it's going to be a brave banker who says, I'm going to overturn this view and I'm going to supply this person with the finances that they require, because in case it goes bad, everybody will now fall on their heads and say that you did a stupid mistake. And therefore, the safe bet is to say that, look, bank A and B said no, I'm bank C. I would also just follow the trend and deny the loan. The same thing is also happening with predictive policing, which is based on demographics. And this can actually alienate innocent targets. So even if you're not a criminal, you actually start behaving like criminal because the system is and the society is treating you like that. So even if you're being treated as a criminal, even if you're not, you might as well become that because hopefully you will get some more returns in that process, right? Similarly, you'll see that many of the companies nowadays are using software to do just-in-time scheduling practices for many of their workers, either on the shop floor or on the assembly line or in the front counters and so on. But this has resulted in people being treated like machine parts. And another example that is particularly dangerous and that we have all experienced in our daily lives, especially with all our WhatsApp news and groups and so on, is the proliferation of fake news on social media channels. And this is with the intention of pushing an opinion slant or pandering to a particular section of society. You can also exert peer pressure through Facebook likes and other such responses to media posts, especially by those in the public crosshairs. Just look at the recent Lok Sabha elections, which happened this summer. The exit polls, not only did they get it wrong, they got it spectacularly wrong. So we can always understand if there is some degree of variance because all these polling, the estimates are random variables which come with a mean and some degree of error bar around them. So error is certainly going to be there. But what you would expect is that the error is going to be small, okay, a few percentage points here or there, but not the kind of huge discrepancies that we had in the expectations. And notice again, this was not just by one exit poll. All the exit polls had a common feature. They got it wrong. So I think except for Yogendra Yadav, who was the sole shining exception, everybody else got it completely erroneous. And notice that here the question is very simple. Okay, it's not even a complicated scientific study or something that is requiring huge amounts of data or that requires deep analysis. All that you're asking is, in most cases, just a Boolean question that are you going to vote for party A or are you going to vote for party B? It's just a binary question here. But because of these serious mistakes that were made in these exit polls, it had a huge impact on the stock market, and many small retail investors got badly burnt because they put faith in the outcomes of the exit poll. So, in conclusion, data science is like nuclear power. It has enormous potential for benefiting mankind. No question about that. But we need to recognize that it also has equally destructive power for ruining society. So it is a potent weapon that needs to be used with commensurate care. So there are 3 specific recommendations that I would like to make in this regard, which follows up on what we discussed already in the break. Firstly, data science should be used as a tool of last resort to validate a hypothesis that you already had. It should not be the one creating the hypothesis. You as the human scientist should be making the hypothesis and then looking at the data as essentially a proof technique. So data science should be a tool of last resort, not first. Secondly, the tool should be a support and not a substitute for domain expertise. So you always need the basic scientists, the domain people with the domain knowledge, to be able to look at your data and your outcomes and to, in a sense, validate whether they make any scientific sense or not. Because otherwise, we can easily come up with ridiculous outcomes, which would be plain common sense for people within that discipline, that this can obviously not happen. Like as I showed you with the 100-meter sprint, any medical scientist would have told you that this is impossible to happen given the physiology of the human body, that eventually your performance tapers off. Initially, you have a quick improvement, but after some time, there is only marginal returns that you have. So there will be, the curve will actually flatten out. But if we just use regression lines and extend them in a linear fashion, then of course we'll come up with outcomes. Many of them are exciting outcomes, but usually they are also false. So it's very important for computer scientists to not have this arrogance that if I have programming tools and if I have data, I can come up with scientific answers. We should be the co-pilot or the assistant to the domain scientists. They are the heroes and the heroines, and we should be the best supporting actor, but not the best actor. And that is very important to remember, because with the current availability of computation, current availability of data cheaply, there is an unfortunate temptation to say, I know best. And simply put, computer scientists know absolutely nothing about natural sciences. So it is very important that the team has people, experts from all disciplines, especially the domain. And then certainly the computational scientist plays a big role, no question about that. But as I said, it's very important to realize our role in this. It should be the best supporting actor, not the best actor. Finally, we should always verify that the tool outputs are compliant with science and not with cherished biases. So in the Indian context, we should treat with great caution these claims that we have of overnight Cinderella-like transformations of young graduates into data scientists. Simply put, there are no quick fix substitutes for acquiring the requisite skills in the application domain and in the mathematical foundations. For example, to be a good data scientist, you must have undergone several courses in statistics. It would be at least a 3-year program, if not more, to become a good data scientist. But we all want this immediate gratification where we say that in a short period of time, I'll suddenly change myself. No, you have to pay the dues. And science always requires hard work, spending a lot of time, spending a lot of effort to understand the foundations of the field. And we cannot discard that just because we have an easy mechanisms nowadays for playing with data with computational tools. So data science should not be reduced to pedestrian familiarity with software environments. It deserves better, much better. So now let me come back to the question that I had posed in the title of this talk. Is there a difference between data science and astrology? And the answer is yes, there is a big difference between data science and astrology. Astrology is more accurate. Okay, so with that, I'll thank you for the patient listening. I'll now hand it back to the moderator, but I'll just leave these books up on the screen for those of you who would like to know more about the correct use of data science. So with that, over to you, MD.
Oh, thank you so much. That was fantastic, Jayant.
Sure.
I mean, it was
Thanks very much.
it was really captivating. Before I know some questions have come up on the Q&A. Before that, I had a couple of things. You had so many examples over there. I want to just pick one of them.
Sure.
The university ranking one. I think you also mentioned the local college NMKIT, I think.
Yeah, KRV.
Which actually which actually took the thing of taking third-class students and
Right.
now, is there a bigger bias towards using data which is easily available? Because to measure real improvement in a student is hard work.
Right.
Okay, is that
Right.
also driving a lot of these kind of bad practices?
Also, I think what has happened is that there is many of the universities, rather than actually improving themselves, have resorted to gaming the system. So they look at all the parameters of the rankings and they say that, okay, how do I improve this particular feature? And each of the features has a different weight. So for example, one of the important features is, do you have international students or not? So many of the Indian institutions have now gone to the extent of saying that, let me have some token representation from outside the country, just so that I fill that particular metric. You're not really doing it because you're reaching out to the rest of the world. You are reverse engineering your own academic programs as trying to retrofit it to maximizing the features that are present in the rankings. And this happened even in the USA Today rankings in the US. I think there was a Clemson University, which again suddenly shot up in the rankings. And that's because they basically looked at all the features and said, okay, I know how to maximize each of them. I'm not changed education in any way, but I can essentially game the system to get good numbers here. And in that way, I can make sure that I look very good. And everybody is obsessed with just the numbers. There are two problems with rankings. One is that firstly, are they the right rankings in terms of the sequencing? And the other is that many of the rankings are very close to each other. So if I say that IIT Madras is first and IIT Kanpur is second, I hope there are more people from IIT Madras here than Kanpur, then it actually means that maybe one is 99 and the other is 98.9. There's really no difference. They're all in the same equivalence class. But we get very hung up saying who is one and who is two. But if there is only a fractional difference between them, then it's very likely the next year they will swap their positions. In fact, this happened between IISc and IIT Madras. There was one year where IISc was a little ahead of Madras, and the next year it went the other way. And there was great consternation in our campus saying, oh, yo, we have gone from first to second. And I told them nothing has changed. These are institutions that have gone for the last several decades. You cannot change them overnight. They are elephants. They move slowly. It is just that your measurement methodology has given you a random variable which has some degree of error and is going to keep moving. But you're both very good. That's all that you need to say. There's no need to compare them. And as I said, the other cases, if you look at the NMKRV College, they are actually doing a huge transformation change in the student where they're deliberately taking weak students and making them do very much better. Whereas if I am a top university and just cherry picking the best of them, so if I am a Stanford, MIT, anyway, else I get the best students. So with or without me, they're going to do very well because they're motivated on their own. But if I can take a weak student and convert them, I would put a much more value, which none of the rankings look at. The rankings don't look at the outputs. They don't look at the inputs. They don't say, where did you come from? They just say, what did you produce? And what are your rankings, how many papers you had, what the citations you had. But if you took a rural student and got them to publish in Nature, that I think is a miracle that you have achieved, because from with all the data, the difficulties and the systemic problems that they have come through, and still being able to achieve this is a complete transformation and not something that can be taken lightly, but we don't give any value to it. We are only looking at
And the root cause
outcomes.
really is in the
Yes,
root cause is in the institutions which are doing the rankings, really.
exactly,
I mean,
exactly, right.
Yeah,
right.
so that's where the root
And
cause is, and
unfortunately, our
everybody's aligning
government
to
has
that.
also fallen prey to that. And they all
Yeah,
keep telling you, oh, you are number 2 this year, and you went back to 3 last year, and so on. I think there's a Professor P.R. Kumar who's used to be at University of Illinois at Urbana-Champaign, who's very well-known professor of electrical engineering. He came and said once that if you can wake me up in the middle of the night and I can give you better rankings than any of these other tools that claim to do it based on data.
Sure. Okay, a bunch of questions have come up, Jayant,
sure.
so I'm going to quickly go through them.
Sure.
First one is, it was mentioned that skepticism is important for researchers. Can you please suggest some ways how researchers can improve on this important skill?
Right. Yeah. So, for example, as I showed you earlier, you should always do a sanity check that despite you are having a machine learning model which looks very good, throw garbage at it and see if the same outcomes come. Then it means that what you did actually had made no difference. It was just a cosmetic exercise. Okay? So you also need to look at extreme boundary conditions. So not just look at the representative case, look at the boundary conditions. And so, for example, if your machine learning model tells you that the probability is minus 0.2, clearly something is wrong. Okay? It may be doing things well in the middle, but at the extremes, it may be going haywire. So you need to ensure that at least all the boundary cases do not violate the laws of physics and mathematics. And often the boundary cases are easy to manage because of the fact that many things go to 0 or go to some maximum. You can actually then do the modeling very accurately. It's in the middle that it becomes a little harder because of the various connections. But it's very important to check the boundary cases and saying that if everything is like this, or if everything is the other extreme, then what would happen? Okay, so if in the Bangalore traffic, all of them were auto rickshaws, or if in the Bangalore traffic, all of them were buses, then does this still match with what I would expect? So you can do many of these sanity checks in advance to make sure that the model does not break down beyond what you have just seen. And something else that you could also do is to go and give this model to some other colleagues of yours and say that, can you try your data on this and see whether it makes sense to you with outcomes without telling them what the model actually is. So this could be some kind of blind testing or crowdsourcing or whatever else. You could try many of these things to make sure that you don't make obvious errors in the outcomes. And very importantly, can you check that the performance graphs that you have, at least qualitatively, do they obey what was your initial intuition? Does something move exponentially? Does something move quadratically? Does something move logarithmically? Does something move concave fashion? That at least your gut feeling is usually correct. So given that, if the data says differently, either your intuition was wrong, which is also possible, but I would bet much more often on your stomach than on the data. So even if you're wrong, it means that you have observed something now which goes contrary to conventional wisdom. So you can now do out of the box thinking to be able to explain that. Okay? Like, for example, the anomalous expansion of water is well known. That's a genuine phenomena. But if you had done it just by data, it would have looked wrong, right?
Correct. Okay, cool. Let me move on. The presentation is so good that it's not just the PPTs that we want the recording. I think the answer to that is yes. I think it will get published in the next few days. So that's great. Couldn't there be cases where data science is used to predict or come up with a hypothesis which can be validated by domain experts who try to find casual links based on their knowledge? Sometimes there may be patterns and correlation generated by ML or AI that may have been missed by domain experts. So can it be can we have a collaborative way of working? That's a question.
Right. There's certainly a well-taken point that it is possible that we have missed some very subtle and nuanced patterns, but it's important that the domain scientist approaches it with great skepticism and says that I don't really think this is so, and actually does a serious study to convince them that what you have seen is a real phenomena and not an artifact of a mistake made in the methodology with the data. So it's also there's a danger if you already tell the outcomes to the domain scientist. There is a natural human tendency to somehow force fit your own thinking to match that observed outcome. So the problem also is that we are not completely independent in our thought processes. We get aligned with whatever we are seeing. And if somebody says something, we tend to like to agree with that and say, hey, now the data also is matches with whatever is the expectations. So ideally, they should be given a blank slate and said that, do you think this could be true? And they should answer without looking at the data and saying that, for example, if you say we have reverse flying aircraft, it looks which was something which is very popular in India and was debunked by one of the faculty in the aerospace department, Professor H.S. Mukunda in IISc, who did actually a detailed study to show that scientifically this is ridiculous. But in order to do that, he had to approach it by looking at it ab initio and saying that, do the laws of aerodynamics, do they support reverse flying aircraft or not? And he actually showed that it is not possible to do it because of Bernoulli principle and many other things. But it's important that we don't get sucked in where we are already told the answer. Then we have a human tendency to retrofit everything to match with that. So some ideally you need if you do in these medical trials, half the patients are given the drug and the other half are given the placebo. It's important to have that kind of a separation to verify whether there is a genuine statistical intervention which has impact or is just an artifact of a clumsily put together model.
Oh, that's a fantastic idea, actually, of going to domain experts and presenting this and saying without the data, saying, do you think it's true? That's great. Okay. Fantastic talk, Jayant. You have talked about ML models mostly. What do you think of Gen AI models? It seems like
okay. I was waiting
they're
for
going
that
to take
question.
over the world.
Yeah, I was waiting for that question. Yeah, so if you look at the AI models, there are three types. One is the predictive AI, which was been holding center stage for the last decade or two. And now in very recent times, there is Gen AI, and then there's content moderation AI. Now in generative AI, I think it's a little better than predictive AI because it's just saying that I'm creating things for you. Like you may be able to create a waterfall that goes backwards. Okay? We know that that's patently false and goes against laws of gravity and so on, but it's just fun to make up these pictures or to create new ideas or to get some answers for basically questions that could be answered from the web, but you now get it in a more conversational manner. So I think in the generative AI, there is much less danger, but in predictive AI, which is what is mostly used by much of the world, because you would like to, I mean, the ideal way is that if you had a model to predict the stock market, then apart from MD, the rest of us also could become millionaires, right? So then we should ask the question, how come we just didn't do the stock market first and forget the rest of it and we'd all become the Ambanis and Adanis and so on? But predictive AI is very dangerous. Generative AI, I think, is in a sense much more amenable to being used without having undue or strange expectations, because you know that when you're creating it itself, that in a sense it's being synthesized and it is an artifact of something that is coming out from imagination. So in that sense,
But
I think
suppose
Gen
you know,
AI is LLM models are somewhat easier, and we already well know that they're prone to hallucinations, and most of them come with the terms and conditions saying that don't trust me and I might be wrong. In fact, if you look at ChatGPT and so on, the first thing it says that, oh, I'm so sorry, I might have made a mistake. So they're extremely apologetic. And what I have found is that if you say shabash to them, they do very well.
But by the way, I've seen people using LLMs to make predictions. Okay.
That's would be dangerous. Yes, if you just make it to do your homework, then it's fine. But if you use it for making predictions, then then we are falling into the same trap of predictive AI, right?
Correct. Okay. Let's see. Let me quickly go through. Okay. Which stakeholders should be educated along these lines to make the right course corrections to make the most positive impact? How do we reach them, teach them effectively with this, reach them with this message? I think it's a great question because this is prevalent. I mean, just as an example, by the way, you did talk about the one day data science course at the back of autos. Remember, people are falling for it because they have, at least in their minds, they have whether there's real data or not. they think that that will get them a job, and that's why they're
Exactly.
going
Right.
after
Right.
it. Which means
Right.
there are people out there recruiting,
Yeah.
people with the one-day course. So
Right.
how do we
Right.
educate the stakeholders?
Yeah, I think this is always a tough call because, especially in India, we look for quick fixes. And we say that, okay, we want to get immediate gratification in many of these things. But what is important, I would say that even in the academic institutions, I don't think sufficient importance is being given to statistics. We often have people teaching linear algebra, we have people teaching the geometric analysis, we have people doing calculus and so on. But the number of statisticians, if you ignore the ISIs, which are meant for statistics, in many of the institutions is particularly weak. And even the data science departments don't have honest to goodness statisticians. You have people who know statistics and doing some domain expertise, but it's very important to have a core statistician in all the departments who are claiming to do data science. And hopefully those are the people who will stop you from making all these kinds of basic errors like right censoring or looking at conditional probabilities and making them equivalent to independent probabilities and so on. So it's, I think in our hiring practices, we don't give sufficient importance to statisticians. We are so enamored of the ML applications that we forget that there should be essentially like an audit committee, which is this like the ISI marking that the Indian government does for various products. You want a statistical auditor in all your departments to make sure that you have not jumped to the wrong conclusions. And I see even that missing in many of our institutions currently, even in a sense, the premier institutions. And certainly, if you look at all the state colleges and universities, not enough emphasis is being put on the underlying mathematical foundations. It's much more on the application side and on the tools and saying, look, all this works great. But the skepticism and the fact that mathematical models can give you sanity is in a sense being pushed under the rug. And I think that is very critical. And even in the companies, of course, again, I would highly advocate that statisticians who are, who are essentially full-time statisticians should be hired, not those who are doing it on the side as apart from their regular scientific work. But full-time statisticians are very important to have. And in fact, India has a very strong tradition of statistics. We have all the ISI institutions which go back a long way. We had the planning commissions, which did tremendous data analysis. So we have a very good tradition, but that's been largely in the ivory tower and in the government ministries. But it should have percolated to the private institutions, to the state colleges, and to the industry as a whole, that statisticians are a very important sanity check on our wishful thinking. And that's something I would say.
Yeah, and I think even at high school level, the emphasis on
Oh,
probability statistics is very low.
yes, yes, you're right.
That itself, and by the way, humans in general are not very good at probability. We know it, and there are many
Yeah, we
examples
can
of
easily
that.
get fooled. Yes, yes, yes,
Very
absolutely right.
easily
Right.
get fooled.
Yes, even the
We
JE
are at
questions used to be always something that would make us go upside down. Okay, right. You are absolutely right. Yes, it's a very
correct.
deceptive art. Yeah.
Yeah, we are at
Mm.
6:33. So I'm just going to ask one last question from the audience, and then we'll close this. Isn't it the case that many of these mistakes are politically valid? Aren't at least some of these mistakes caused due to obsession with technocracy and disrespect to deeper scholarship, both of which
Yeah.
are tendencies often associated with the political right? Okay. The final question.
Right. Yeah. Yeah. I think the issue is that nowadays we want to claim that we are superpowers very
Yeah.
quickly. Like we always say, oh, we are the software superpower and we are going to be a superpower in this and that and so on. And we always would like to claim that we had discovered this thousands of years ago. But if we just compare ourselves to the Greeks, they have an equivalent or similar mythology. And they're not saying Zeus, the god of lightning, actually invented electricity, right? So fine, you have a good tradition, there's a huge culture, all that, you can take legitimate pride in that. But you should not go to the extent of now saying that we had invented everything in the past. And in fact, Rodam Narasimha was very good at this. He was actually a Sanskrit scholar also. He had read all the texts and he said that it's very important to not go to either extreme. Either should you claim that you know everything and that we had done all the great advances in science had been done 5,000 or 10,000 years ago in India. Nor should you go to the other extreme of just throwing it all away. You need to make a scientific assessment. And in all his work, he actually did that. He would actually go in and say that he would separate the wheat from the chaff. And quite often, in fact, he also resigned from the government at one stage, saying that I cannot support this scientifically. So you need to keep an open mind and not just get swayed, so be in the center, neither left or right. And skepticism is very important, and we should not forget that in science, I think.
Correct, correct. Well, Jayant, thank you so much. This was fascinating.
Yeah, and thanks very much for moderating. It's a pleasure to be with you here again.
Thank you, thank
you.
you.
And thanks to Abha and Sushila and all the others from
thanks to
IITACB for giving this platform.
Thank you. Sushila, over to you.
Thanks very much. When I first chatted with you, Jayant, I knew that this would be an interesting session, but little did I know that it would be such an enjoyable and fun way of learning about data science. So thank you ever so much for your for the session. Just a few key takeaways. I think we started by saying that how methodological abuse results in completely erroneous conclusions and in many cases behavior that is not what we would want it to be. And then Jayant gave us a number of examples of where data is good, the good, the bad, and the ugly of data science, and what the results have been. He actually demystified data science when he said that it's really about statistics on steroids, right? So, and I think you emphasized that again towards the end as we were discussing some of the questions. So in the good, we see a lot of examples of industries like the oil industry, transportation, healthcare, and so on, where a lot of good has happened thanks to data science and its good application. And we also saw the quotation, if you torture data long enough, it will confess to anything. So basically, it's about bringing in biases and so on. And that's where we went and looked at the bad and the ugly of data science as we see it today. Subconscious biases that come in, asking the wrong questions, etc. Those are many ways in which we don't do the right thing by data science. We saw many examples, and some were really hilarious. When we look at it from afar, they sounded really hilarious. From a wide range of areas, research, airlines, musicians, and the age at which they died, and so on. The pharma, creating molecules. All of that, we saw a very wide range of examples. While they gave us a good laugh, they also highlighted the many flaws in our thinking, in the biases that we carry, the mathematical errors, and also concepts like, what are we really seeking here? Is it correlation? Is it causality? What is it that can rightfully be expected from this particular, whatever the model that we are trying to create? So, and then finally, I think we concluded that good data science basically needs to start with asking the right questions. We have to factor in reality. There has to be a deep understanding of the domain. We have to understand the context. We have to be cautious that it doesn't end up with us, creating some self-fulfilling prophecies. And most importantly, validate the conclusions that we draw with domain experts. And then his advice was, data science should be used to validate hypotheses and not to create them. It should be used as a support tool and not substitute for the domain expertise. And very importantly, check for compliance with science and make sure that it doesn't have biases built into it somewhere. For students and those who are attracted by those posters which claim shortcuts to becoming wonderful data scientists. It's important to make sure that you study multiple statistics courses. It is much, much, much more than the tools, and you need to take time to understand the foundations of the field. Of course, Jayant, in his wonderful way, told us that astrology is actually more accurate than data science, and we know why he said that. All right, since we had these questions, I do want to say that all our webinars are recorded and put up on our YouTube channel. So please go there and look for the IITACB videos. You will find all of our videos there. I must say we've had, Abha and we have had a wonderful time hosting these webinars because every one of them has been real fun. We've learned a whole lot, and these webinars have spanned such a wide variety of topics. So you will find them all there. And we will also like to invite you all to join us on our next webinar, which is in the field of astronomy, not astrology. So please do join us. We run these webinars typically on Saturdays at the same time. So yeah, we look forward to seeing everyone again on our webinars. And Jayant, thank you so much for this.
That's
And
my
MD,
pleasure.
MD, thank you for moderating this in such a wonderful way. So all the best to everyone out there. May data science help you in all your, in everything that you would like to do, and that it is gives you much more than astrology would. And with that, thank you and good night.